So let's talk about EIGRP general operations. In this video, we will go over kind of the basics of EIGRP, what it does, kind of how it forms a basic adjacency, and then we'll cover the more details and things like packet types and neighbor types and things like that. So we'll have some videos after this that cover some of the details that we're going to leave out in this video. For example, like passive interface. I might mention it in this video, but not go into it in a great depth because I'll cover it in another video. Now, before we really get started with any of the content here, EIGRP comes in two flavors that we're going to need to know. It comes in what we call classic mode, and it comes in named mode. Now, the primary difference under the hood between these guys is the fact that classic mode is going to calculate 32-bit metrics, whereas named mode is going to calculate 64-bit metrics. And I go into depth in the metric calculation video as to why that is. But essentially, at a high level, named mode is meant to be run on interfaces from basically 10 gig up to, I think, 4.2 terabytes, whereas classic mode was really never meant to talk anything above 1 gig. So if you're running classic mode and you have 10 gig interfaces, you might think that everything's okay, when really it's not as proficient as it should be. If you were to add a 1 gig interface into a classic mode configuration and you have all 10 gig interfaces, let's say you have two 10 gig interfaces going to the same, the same endpoint, right? So let's say these guys are 10, these guys are 10, and then you go ahead and you add a 1, you will find that essentially EIGRP classic mode is going to start load balancing across all three interfaces, because EIGRP classic mode doesn't really understand how to properly calculate metrics of 10 gig plus. So we had EIGRP named mode, which now uses 64-bit metrics. Now, the other piece to this is that classic mode is going to use I want to say regular or traditional configuration, whereas named mode is going to use all address families for everything. So, for example, if you go and you add a summary in classic mode, you would typically do this under the interface. You would say interface Ethernet 00, and then you would go ahead and you would create your summary. Whereas in named mode, you're actually going to do this under the address family interface, right? So the logic there between classic mode and named mode is similar. Actually, it's almost identical, but the syntax is very, very different. So classic mode and named mode are going to be the same and yet very different, okay? The other thing is that both of these protocols can do either IPv4 or IPv6. They can also do both at the same time. The difference really is where you configure it. Again, the syntax there is going to be different. In named mode, you're going to do this either under an IPv4 or IPv6 address family, whereas in classic mode, you're going to do IPv4 typically under the global process, and you're going to do IPv6 under the interface in classic mode, okay? So the syntax here is going to be different, but the logic is the same. So if you can remember classic mode and you understand the basics of how it works, named mode shouldn't really be that much of a catastrophic difference for you. Okay? Now, what I'm going to do is I'm going to draw a switch here. So let's say this guy's switch 1. And let's say that we have 4 connections coming off of this switch. Let's say that this guy's going to be VLAN 1, this guy will be VLAN 2, we'll say VLAN 3, and VLAN 4. Let's add some subnets. We'll say 192.168. We'll say .1.0/24. This guy will be we'll say 2.0/24. This guy will be 4.0/24. And this guy will be 3.0/24. Now, typically on a switch, let's say this is our core switch, typically in the traditional route switch world, what we would do is we would say, okay, VLAN 1 maps back to an SVI, right? So we would say interface VLAN 1, and we would give this guy maybe 192.168.1. And then we would create an SVI here, and we would say maybe this guy would be, 192.168.2.1 or whatever. So we would have these SVIs here that would essentially marry up to the actual VLANs that we created, right? So every VLAN, every layer 2 VLAN is going to map back to a layer 3 SVI, right? And that's typically the way that we do that. And so that being said, let's talk about this neighbor discovery process. So you go into EIGRP and you say router EIGRP, right? So we say EIGRP. The first thing I need to do is I need to pick an autonomous system number, which must match on that particular LAN segment. So in other words, if I want to form an EIGRP adjacency out this VLAN 1, and I have a device out here, let's call him R1 here, and he's connected in on VLAN 1. If he's sending in autonomous system 3 and I say autonomous system 1, it's not going to work, right? So this autonomous system has to match, all right? So now I go in and I say, you know what? I want to redistribute all of my connected subnets. So I say redistribute, and we say connected, and nothing happens. Why hasn't anything happened yet? Because we haven't activated the EIGRP process yet. A lot of people get confused here and they think, okay, this is it, right? No, you've only started to configure the process. You haven't actually activated it yet. And then some people come in and they say, well, I don't know why EIGRP isn't forming an adjacency yet. I'm supposed to send out these hello packets to this multicast address. What's going on? And they go in and say, well, let me try a static neighbor. So they go in and they say, okay, neighbor, maybe router 1 is, we'll say 192.168.1.5, and that's, the IP address of router 5. Who knows? And still nothing happens because we haven't actually activated the process yet. In order to activate the EIGRP process, you need to establish what we call a network statement. And the network statement can be anything. You can have a network statement of all zeros, so you can say 0.0.0.0. That would essentially say enable EIGRP everywhere on everything. You can add a specific network, so you can say network. Maybe I only want it on this interface. I could say 192.168.1.1, and then I would add a reverse mask here of all zeros. Or I could say network 192, I'm going to probably run out of room here, 192.168.0.0, and then my reverse mask can be something like this, with 255s in the last 2 octets. Now, this would say everywhere. This would say only on this specific interface, so I would only enable EIGRP right here. And this network statement here would essentially say this 0, match this octet exactly. This 0, match this octet exactly. This 255, I don't care. This 255, I don't care. So this reads, I want you to activate the EIGRP process on any interface that matches 192.168.I don't care, which essentially is the same as network all zeros and essentially enabling it everywhere. Once you enter the network statement on a particular interface, once your addressing scheme here in your network statement, and by the way, even if you're doing a unicast neighborship, by default, EIGRP is a multicast protocol. So by default, we're going to start multicasting these hello packets to 224.0.0.10. Even if you change that to unicast by using the neighbor statement, you absolutely still have to enter in a network statement, because the network statement is what actually activates the EIGRP process. I think I cover that in the unicast multicast neighbor type video. But anyway, so once we do this, EIGRP starts sending out these multicast hellos out any interface that matches our network statement. This is our dynamic neighbor discovery process. Okay, so these hello packets start going out destined to this address. Okay, now any other devices that we have sitting out here are now listening for that same address while sending out their own hellos on that particular, or destined to that particular address. Inside of that hello packet is the autonomous system number. So when we say the ASN has to match, this is how we actually discover whether it matches or not. Because if it doesn't match, we see that in the hello packet that we are not only receiving, but our neighbor sees it in the hello packet that we are sending, and so the adjacency doesn't form. Okay, so this is the dynamic discovery. You can change this to a static discovery or a unicast relationship by using the neighbor command, and then obviously you're going to have to enter in the address of where you want to form the neighbor. But this has to exist the same on both sides. In other words, you cannot send unicast from switch 1 to router 1, but expect a multicast packet back from router 1. It has to be unicast on both sides in order for you to form an EIGRP adjacency. Now, EIGRP in itself is a Cisco proprietary protocol. However, in EIGRP, Cisco built in what we call RTP, Reliable Transport Protocol. People have also come to call this Protocol 88. This is a Cisco proprietary protocol that EIGRP essentially rides over, and what it does is it ensures reliable packet delivery, okay? EIGRP has to ensure that its packets are delivered and that they're delivered reliably, that they're in order, etc. So what EIGRP does is when we receive something like an update, let me pick a different color. So router 1 here, let me see if I can squeeze this in, sends us down an update. Okay, so he sends us an update, and that update contains all these different subnets. Inside of that update is going to be a sequence number. Okay, and EIGRP may send us an update with a bazillion updates in it. That packet regardless is going to contain a sequence number. Okay, the last packet that we receive that contains those updates in it with that sequence number, what's going to happen is that at that point, what switch 1 is going to do once he receives it is he is going to send back what we call an ACK packet or an acknowledgement. And in that ACK packet is going to contain that same sequence number that we received. So if I send in this update and let's say the sequence number here was 35, the sequence number that I send back is going to be 35. That's how the neighbors ensure that we have this reliable packet delivery between each other, okay? And I'll cover some of this in more depth in other videos. So this is just kind of a high level of how EIGRP is working under the hood. Now, EIGRP uses something called the dual FSM, dual finite state machine. That's what FSM stands for. And dual stands for diffusing update algorithm. This is the algorithm that actually is responsible for the route computation. That long, obnoxious metric that we see in EIGRP. I don't have it listed here. I'm just doing this line to represent it. That long, obnoxious metric that we see in EIGRP, dual is actually what's responsible for calculating that metric and actually making or helping EIGRP. It's not really helping, it's doing it, is actually what's creating our best path selection in EIGRP based on those metric values. So this is actually the metric calculation. Okay, now anytime we have a change in the routing table, anytime we have new updates come in, dual is what's actually going to be responsible for computing those routes and deciding what routes go into the rib, what routes don't go into the rib. It's responsible for modifying the metrics in the rib. This is what actually does that. Now, in order for these routes to go into the rib to begin with, they must first be in the EIGRP topology table. So EIGRP is going to have a database, and it's going to be called a topology table. That topology table is going to contain all of the computed metrics already. So what's going to happen is that as these updates here come in, they hit the topology table. EIGRP runs the dual algorithm against it, and it says, okay, I run the algorithm against it, and I have, let's say, maybe 2 routes, so maybe I'm getting in an update from this direction as well, so maybe I have R3 out over here. Maybe these guys are connected to the same, LAN segment across here. I'm kind of running out of room, but we'll draw it anyway. Maybe these guys are connected to the same LAN segment, and so I get the same update in from this direction for the same subnet, and so this lands in my topology table. Okay, and so now what EIGRP does is he runs dual against this, and he says, okay, which one of these guys is going to go into the rib? It could be both, it could only be one. It's based on that metric calculation that we do, and that metric calculation, of course, is based on bandwidth, load, delay, reliability, MTU, and if you're in named mode, it's also jitter, okay, which is going to be the K6 value. I think I have those on the next slide anyway. Now, again, in order for these routes to even go into the rib, they must be in the topology table first. So I watch a lot of guys deal with load balancing. I watch a lot of guys deal with, how EIGRP is actually receiving these routes, and they find that they can't get these guys into the rib, and they never check the topology table. If it's not in the topology table, it will never go into the rib. It's not possible. Okay, they have to go into the topology table first, and then based on your algorithm calculation, then they will go into the the RIB. Okay. Now, last is that EIGRP is also going to maintain a neighbor database, or what we call a neighbor table, and that's just simply going to contain all the detailed information about your individual neighbors. And I'll go into that in greater detail when we look at the CLI. Okay. So let's go to the next slide here, and then we'll jump into the CLI. I know you guys are getting antsy. So in order for us to form that adjacency, we need to have authentication matching. And that's not just a password. So let me explain what I mean. Classic mode supports MD5, right? Now, named mode supports MD5, but it also supports HMAC authentication. And I will go into HMAC. It also supports HMAC. So what if I'm using HMAC authentication in my named adjacency, but I'm trying to form an adjacency with a router that's only supporting MD5? Well, this is not going to work. I can't form an adjacency there. So it's not just the actual password, which many just, you stop right there, you get tunnel vision and you think it's the password. It's also the authentication type. So not only the type, but the password also must match. Another piece that must match is these K values, and this is what I was just talking about here, the bandwidth, the load, delay, reliability, etc. Now, by default, the only two that you should have to worry about are going to be bandwidth and delay. In fact, if you go out to Cisco's website, and I can't remember the article offhand, but if you look at configuring these in EIGRP and how to change them, I believe there's a note in there that tells you that Cisco only recommends that you tweak the bandwidth and the delay. They do not recommend that you tweak the load, reliability, and MTU. These guys here are kind of like your tiebreakers. Okay, they're not really meant for you to tweak endlessly to modify your metrics. The two that you should really always use are your bandwidth and your delay. Now, one thing when we get into redistribution and we talk about redistributing into EIGRP, these are not in the same order when you redistribute, and a lot of people get confused there. So when you say redistribute EIGRP, essentially, we are looking for the same values. So EIGRP is going to ask you for the bandwidth, the delay, the load, reliability, etc. But they're not in the same order. So be very careful there when you're enabling your K values. A lot of people think that if they're in a scenario where they get K value mismatch, right? This is the wonderful error message that you're going to get when your K values don't match. I'll show you this in the CLI, so don't worry. When your K values don't match, right? A lot of people think, well, let me just say redistribute connected to find what order these go in, because people can't remember what the actual values are in, because when you change these values, you don't see this. EIGRP is not nice enough to tell you that. It just says K1, K2, K3. You have to remember what they are and what they mean, right? And so people say redistribute connected, and they say, okay, bandwidth, delay, etc., and they don't realize that they're in a different order, okay? But bottom line is they need to match, and there's K6 for EIGRP named mode. This is not going to be in classic mode. So if you don't see that, you're most likely in classic mode. Autonomous system number must match. Remember that this is in that hello packet. So in the hello packet is actually going to be our ASN. And if in that hello packet, when we sent out to 224.0.0.10, if we don't see the right ASN in that packet, we're not going to form an adjacency. The other piece that needs to match, or that I should say needs to match, is the LAN segment. In other words, what needs to happen is that I can't, let me draw a picture of what I see most often. I can't have a 172 subnet over here and a 192 subnet over here and have these guys form an adjacency with one another. That's just not going to work. And where I see this a lot is where people mess up their layer 2 VLANs. So accidentally they leave this guy in VLAN 10 or VLAN, let's say 192, for example. And, as they're trying to get these guys to talk, they put this guy in VLAN 192, and it's a completely different subnet altogether. And inside the hello packet, we cannot have these different subnets or these different LAN segments form an adjacency. You're going to get not on common subnet. Not on common subnet will be the error message that you get. And when this typically happens, most of the time it's going to be VLAN membership or the incorrect IP address somewhere on that device. Now, the last thing is that you can't use secondary addresses for your EIGRP adjacencies. You can only use the primary address on an interface. Okay, now last thing I want to talk about really quick before we jump into the CLI is the timers. EIGRP by default is going to use two different timers, and it's going to be based on the interfaces that you deal with. On slower bandwidth links, so for example serial interfaces, they should be using 60-second hello intervals by default. Most of the time you're not going to see this anymore because most of the interfaces that we have are high bandwidth links, 1 gig, 10 gig, 40 gig, 100 gig, etc. And you're going to see a 5-second hello timer. Okay, now the hold time, in other words, how long we're going to hold on to that EIGRP adjacency, is going to be 3 times that hello. So in this case, it's going to be 15 seconds. So we'll basically allow ourselves, we'll essentially allow ourselves to miss 3 hello packets before we go ahead and drop that adjacency. So with that being said, covering all that theory, let's go ahead and jump into the CLI and let's cover the same bases only at the command line. So let's go ahead and actually get an EIGRP adjacency going between routers 1, 2, and 3. We'll call this EIGRP 1, 2, 3. We'll use named mode over here on router 2, and we'll use classic on router 1 and router 3, similar to what we did in our metric calculation video. And we'll talk about the neighbor discovery process. We'll light up a packet capture, and we'll take a look at RTP. In fact, let's do that now. So we should see Wireshark pop any second now. There we go. Let's turn on EIGRP filtering here so we only get those packets. Let's bring back our CLI. Let's go ahead and let's actually get an EIGRP adjacency going. Actually, you know what? Let's include, just for kicks, let's include router 5 as well. Just why not? Who cares? Okay, so let's go over to router 1. And we'll say, actually, we can start at router 2. Let's wake them up. Config T, router EIGRP. We'll go ahead and just call this name. And we'll say address family IPv4, autonomous system. And here's where you're going to pop in that autonomous system. Now, here's the thing that a lot of people always wonder and to get confused about in EIGRP is the name for named mode does not have to match between your different configurations. So if we had named mode over on router 1, it should still form an adjacency. Even if we, if we did router 1 for the name and we had R2 for the name over here, it should still work. We'll get more into that as we deal with named mode in a specific video series. So don't worry about that. But I just want to point that out, that it does not have to match. But what does have to match is essentially your autonomous system here for 1, 2, 3. So I'm going to say network, and we'll just say network all zeros. And say show run section router EIGRP. And here is our named mode configuration. Now, what I'm going to do is I'm going to say debug IP packet. And what we should see is we should see ourselves sending a packet going towards the destination of 224.0.0.10. So this is multicast traffic that we're actually using for EIGRP. We're sending out this multicast, we're sending out this hello packet destined to this multicast address of 224.0.0.10, and the source is obviously us, right? So you'll see the different interfaces that we're sourcing it on. This is the LAN segment connected to the switch. This goes over to router 4. Okay, now what I want to do is I'm actually going to go to router 1, and I'm going to say config T, router, EIGRP, but I'm going to say 1, and I'm going to say network 000. And let's actually, what we'll do here is we'll actually say on all, and what I'm going to say is debug EIGRP packets, and I want to say hello. I only want to look at the hello packets, and I want to see if we are seeing any inbound hello packets from router 1, and we're not. Router 2 is only sending hello packets. We're not seeing any inbound hello packets. Let's take a look at router 1. Let's say do debug EIGRP packets, and we'll say just the hello. What we should see on router 1 is we should see the same type of configuration. But I want to do here is say interface E01. We'll go ahead and shut this guy down, and I'm going to say do debug IP packet. Let's see if we see the inbound hello packet. So here's the source. Let's say do on all. So when we were looking at the debug EIGRP packet, we did not see the received hello packet, right? We only saw the sending packet that we were sending, and we saw it every couple seconds, right? But if we do a debug IP packet, take a look at this packet here. You can see that we received a packet, a hello packet on Ethernet 00. That's the interface that connects R2 to R1. That destination IP address, that destination multicast address was 224.0.0.10, but take a look at the source. Who was the source? Who was the sender? The sender was router 2. So we are actually receiving these packets, but we couldn't see that under the EIGRP debug. We saw that under the debug IP packet. So we are receiving these debugs, but we're not, or these hello packets rather, but we're not actually able to form an adjacency. Well, why is that? Because our autonomous systems are different. So I'm going to say no router EIGRP 1, and you'll notice that right here, there's no error message under these specific debug commands, right? So if I say router EIGRP, and I spell like a normal human and say no router EIGRP 213, dyslexia in action, router EIGRP 123, and I say network, and we go ahead and enable this on all interfaces, you can see that automatically we have an adjacency that comes up. Okay, now what I want to do here is I want to actually say interface E01 and no shut this guy. And I want to talk about this reliable transport protocol for a second. Let's go to our packet capture. Let's scroll all the way to the bottom here. I think we can actually stop this so it doesn't continually scroll on us here. And let's take a look at something. We had an update. So we had an update here, go from router 1 to router 2. So this was the address of router 1. We had an update go out to router 2. What was in that update? Nothing. Let's find one. Here we go. So this packet here. So router 1 sends out an update. If we take a look deep inside this update, we can see all the internal routes that essentially router 1 sent out. Let's take a look at this sequence number. In here, we should see a sequence number of 2. So here was this update. It went out to this multicast address. This was from router 1. Let's see if we can find the ACK packet from router 2. Let's see if we can actually find it. What we're looking for is we're looking for the source address of router 2. And here we have it. So if we see the source address here, router 2, the hello ACK packet, that's an acknowledgement, check out the acknowledgement number. So the acknowledgement number is 2. If we scroll up back and we try to find at least the right update, I think it was this one, the sequence number was 2. So when router 2 received the update that was sent in via multicast from router 1, he sent back an acknowledgement, and that acknowledgement had the sequence number of essentially what he received. Okay, so the updates we can see here are going to go via multicast. So router 2 is going to send out an update via multicast. Router 1 sent out an update via multicast. You can see here was a unicast update that went out from router 1 to router 2, along with a ACK packet. So here you can see the sequence number here was a sequence number of 2, and you can see here that the sequence number that went back was a sequence number of 2. So here we have that reliable transport protocol actually running. But it goes even further than that, because if you highlight one of these packets, I mean, just pick a hello packet, you can pick an update packet, you can pick an ACK packet, pick whatever packet makes you happy. And you expand out the IP header, and you scroll down a little bit, you're going to see that the protocol that's actually running is EIGRP, Protocol 88. And this is what I was saying before, that Cisco has embedded its very own protocol to ensure this reliable delivery, and it's called RTP, or Reliable Transport Protocol. So you can see that Protocol 88 actually in the packet when we look at it. All right, now let's take a look at the EIGRP topology table, or the neighbor table. Now that we have some neighbors, let's say show IP EIGRP. We didn't get router 5 in here, we may not. Let's show IP EIGRP neighbors. Sorry about that. Now you could pop in some detail here, and this will expand out the version that you're connected to. So version 14.0. So this will, this will give you a little bit of details, but mainly what you can look at is just the plain detail will give you these numbers here, and it's important to know these details. Okay, and the reason why, actually, let me get router 3 up and going, and I'll go back to that in a second. Config T, router EIGRP 123, network all zeros. And let's go back to this, and let's say EIGRP neighbors. So let's go through this a little bit. First of all, this H field, what this is going to do is this is going to give you the list of neighbors, and it's going to be in order of how they're learned. And 0 is always going to be essentially the first one. So we learned router 2 first. He starts at 0. We learned router 3 second. He starts at 1. And you're going to see these in order of how they're learned. The interface here, I'm sorry, the IP address, I missed a field. The IP address here, what that's going to do is that's going to give you the IP address of your actual neighbor. So we have 10.1.3.3. You can see that's our IP address here. We have 10.1.2.2 right here, and you can see there's the IP address there of router 2. So these are the addresses of our particular neighbors. Then we move over to the interface. Now this interface is the interface of where we learned the neighbor, meaning that this interface here, Ethernet 00 for router 1, that's the interface here where we essentially learned that actual neighbor. Okay, same thing with E01 over here for router 3. Now we have the hold time. Now these hold times, again, is going to be 3 times whatever the hello time is. And by default, the hello time is going to be 5 seconds. Okay? Now, the 3 times that 5 seconds is going to be 15. So the whole time here that we're seeing is 15. And it's okay that they decrement. So if I hit the up arrow, you can see that there are different times here. You can see that you know, they're changing. That's fine. What we want to pay attention to is that they don't hit 0. If they hit 0, we're going to drop the neighbor. The uptime tells us how long that particular neighbor has been up. And then we have the SRTT. What that stands for is the smooth round trip time. Okay, it took me a minute to just kickstart the brain. So this is the smooth round trip time, and what this is how long it takes us in milliseconds, how long it takes us to essentially send and receive a reliable EIGRP packet. So this is letting us know the time in milliseconds it takes for essentially RTP to do its thing. Okay, then we have the RTO. This is the round trip timeout. Okay, so basically this is the amount of time we're going to wait before we retransmit a packet. Okay, so if I don't receive, so if I send you a packet and I don't receive an ACK packet back in this amount of seconds or in this amount of milliseconds, I'm going to go ahead and I'm going to send you another packet. I'm going to retransmit it. Now the queue count here, this should always be at 0. If you have a properly functioning EIGRP domain, this should be at 0 at all times. This here, this queue count, let me grab my pen here and just write them in. The queue count is going to include update packets. It's going to include query packets, and it's going to include reply packets. So if we see that queue count as anything other than 0, what that means is that we have one of these 3 packets, or it could be all 3, it could be multiple. We have that many packets in the queue that we are not able to send between our particular neighbors. So that means that router 1 was not able to send, you know, 5 packets to router 3. That could be an issue. In fact, it would be an issue for whatever reason. You'd have to trace that back and find out and troubleshoot why I'm not able to send packets to that neighbor. Now the sequence number is going to be the sequence number of the last EIGRP packet or reliable packet that essentially we received. It lets us know what sequence number we are essentially at when we want to send back that ACK packet. Okay. Now, before we jump into the topology table, there is a debug command that I just want to show you really quick, and it has to do with the topology table. It's debug EIGRP, and then it's FSM here. If you want to debug that you actually are running the dual algorithm on your EIGRP updates, you could debug FSM. It's going to give you not the metric. It's not going to give you, you know, all of the numbers. I mean, it'll give you numbers. It'll give you values, but it'll at least let you know that you're running it. You don't necessarily, you know, you're not really going to get a ton of it as you're debugging, but it'll allow you to actually see that you're getting some routes. So if I say config T and I say interface loopback 10 and we say IP address 10.10.10.10 and I say 255.255.255.255, let's say do on all, so we don't keep getting that debug. You can see here that it actually told us that we ran the dual algorithm. So it lets us know, you know, some of the values that essentially it was calculating. It let us know the metric that it was calculating, and it says, you know, hey, dual, we installed this route via 10.1.2.2, and we should see that in the routing table and in the topology table. And that leads me to the topology table. Let's say show IP EIGRP. By the way, you can say a really cool command that you can do is show, I think it's EIGRP traffic. I always get messed up whether it's show IP EIGRP traffic or EIGRP traffic. This will give you some of the statistics based on EIGRP, your adjacency. So it'll let you know how many ACKs you've sent and received, how many updates you've sent and received, how many hellos you've sent and received, let you know for which specific autonomous system number we're talking about, let you know any of your queue counts here. I mean, it lets you know pretty much everything you really need to know, you know, with a quick down and dirty, here are your outputs, here are your statistics. Are we stuck in active? Are we actually querying for any lost routes? So this is actually a great command. But let's say show IP EIGRP topology. This is our topology table. This is essentially where we come to see whether routes meet things like the feasibility condition. Are they going to be put in our routing table? They have to be listed here in the topology table before they can actually be added into the RIB. Okay, now here's the thing with this. A lot of people get confused because they'll come in and they'll say show IP EIGRP topology, and they'll add the prefix on the end of it, and then they'll actually take a look at these more detailed updates. When you're looking at this piece of the topology table, you are actually looking at the update advertisements that have been sent to you. You're looking at the actual updates for this prefix. It does not mean that they are in your topology table. When you say show IP EIGRP topology table, you will get this output here. This is where they need to be. It is very possible for you to have multiple listings for a prefix, in other words, multiple updates for a prefix, and only have one of them added into your actual topology table. So don't get confused between the two commands. This piece is just taking a look at your topology table. When you add the prefix on the end of it, you're actually looking for the updates that have come in for that prefix, in which case, for this prefix we have 2. But if we went down the road of messing with the metric and removing this, we might still see 2 updates, but if we didn't meet the feasibility condition, you wouldn't see 2 prefixes in the topology table. I'll get into that in another video, but I want you guys to understand that and be aware of it. Okay, now let's take a look at these K values here for a second. Let's say config T, and I'm going to say router EIGRP 123, and I'm going to say do show run all section router EIGRP, and what we're going to find is that we have, where are they? Metric weights. These metric weights are essentially your K values. So you have K1, K2, K3, K4, K5. This value here is actually the TOS. So let's do metric weights, and if I hit the question mark here, whoops, sorry, I'm not in my, so we'll say router EIGRP, I should be in there, and we'll say metric weights. And if I hit the question mark here, I'm not sure, oh, I forgot the M. This is actually the type of service. So this is the TOS, okay? Now, generally speaking, this is always going to be 0. We're not really going to mess with this. What you'll see here is that if I do K1, as I go through this, it doesn't tell me whether this is bandwidth or not, right? Like I was explaining in the theory portion of this video, this doesn't tell me whether it's bandwidth or not, it just tells me K1. I want to go into EIGRP for a second. EIGRP, suppose I'm in a scenario where I don't remember this and I say, well, let me say redistribute EIGRP, and I'll just pick another process number, and let me add the metric, and let me see what this actually is. So if I say bandwidth, right, let me just add a value. The next thing that comes up is delay. So the redistribution commands are not in the same order as the metric weights, because K1 is going to be bandwidth, so let me just leave that on. K2 is going to be load. But in the redistribution commands, the second value that you would add is going to be delay. So when you do the redistribution, so we'll just say delay 1, we'll say reliability 1, we don't really care. I'm just pointing out that you're going to see bandwidth, load, reliability. You're going to see all these same, so bandwidth, delay, reliability, load. You're going to see the same, and then last is going to be the MTU. You're going to see the same K values in your redistribution, but they're not in the same order as the K values for your metric weights when you're actually going to try to form an adjacency. So K1 would be left off by default. This would be load. Then we have K3. This is going to be a value of 1. We want to turn it on. This is going to be your delay. Then we're going to have K4. This is going to be, let's see, bandwidth, load, delay, reliability. This is going to be off. And then we're going to go ahead and we are going to, what's this, K4? So that's going to be, oh, come on. So let's see, we have bandwidth, load, delay, reliability, and then we're going to have MTU for our K5. Now you'll notice in EIGRP classic mode, we don't have a K6, but in named mode, let's say do show run section router EIGRP. Let's go into named mode. Let's go into our address family. Let's say metric weights. And you can see here, let's do TOS, we'll do 0. We'll do bandwidth is going to be 1. Load is going to be 0. Delay is going to be 1. Reliability is going to be 0. MTU is going to be 0. And then we have a K6 value. So we have bandwidth, load, delay, reliability, MTU, and then K6, which is going to be the jitter value. Now, if I go ahead and I enter in a a different metric weight. So let's do that here. Let's say on router 3, we'll say metric weights, and let's say 0. Let's turn off bandwidth. Let's leave off load, and we'll leave the rest as default. What's going to happen here is that our metrics are going to change, and what we should find is that we have a K value mismatch. So these metric weights have to absolutely match. So if you see this message, it's an indication that somewhere, somebody, for some reason, has tweaked the metric values or the metric weights inside of EIGRP. Okay? So that's it for this video series, guys. I'll have another video, just a quick one on EIGRP timers. We'll take a look at that in detail in another video. Hope you guys enjoyed just learning the basics and the general operations of EIGRP. See you guys in the next one.